So thanks a lot, everybody, for participating here. And it's my pleasure to introduce John Sheehy, who will speak to us on using homology to analyze sensor networks. Thanks.
Okay, thanks for having me. So I'm not really going to talk about sensor networks. I'm going to talk homological sensor networks. I really work on sensor networks like physical sensors. Sometimes don't really agree with maybe some of the models we use for sensor networks, homological sensor networks, but really think of these results as results about data and talking about sensors and samples is a natural thing to do. And it really starts back with this. I need some way to advance. This Neely, Smale, and Weinberger on homology and inference. So probably familiar with this paper. They were looking at the problem of some submanifold of RD gives just a finite point. Now, in general, very ill-posed. You could have a whole or some kind of extra topological feature in the manifold at some scale that was smaller than your sampling. So they had to have some sampling conditions. And under good conditions on both the fold itself and the density of the sampling, they show this union of balls has the homology, in fact, has the same homotopy type as the manifold itself. And so in computation, compute the of the complex or the nerve of this union of balls. And that's the simplicial complex, which simplex for every common intersection. So edge for every pair, a triangle for every three-way intersection. So that gives an effective way to compute of the manifold from just the samples. But some natural questions pretty immediately arise. The first being, what should the radii be? The radii, that it depends on the sampling density, but also on the parameter shape. So the main parameter they use, they call it the condition number. It's related to the injectivity radius of the manifold. It's also sometimes called the reach of the manifold. But that is also something that you don't know in advance if you just have some. The other that comes up, and it came pretty around the same time, was whether smoothness was really necessary. And one of the best answers to that came in this work by Eric Chazal and Andre Luthier. Instead of trying to infer the homology, say, manifold, they just had an arbitrary compact RD. The only assumption they made, rather than smoothness, is that there were no critical points of the distance function nearby. So the idea is going to be similar in that they're going to use a union of balls. And let me just clarify what I mean by the critical points of the distance function. Here in this little picture, inside the triangle, there's a point, and that point is a point of the distance that the boundary is shaped. In this case, the ball around that triangle represents the points of equidistance, and so there's 3 points of equal distance from the point center, and this point is inside the convex closure of the point. It's inside the triangle, and so any point that's inside the convex closure of its nearest points on the set is the critical point, the critical distance function, and the weak feature size, as well, and Luthier defined it, is the minimum points set of the distance to the nearest critical point. As long as that distance is bounded, this gives us a scale which we can unions of balls at that scale to infer the homology of the whole set. But another trick they had to add here, which really was necessary, was to use persistent homology to eliminate noise. So the non-smoothness made it able to infer the homology, but you couldn't infer it directly from the union of balls because some sharps could cause small little bubbles here, like I've drawn. In, can anyone see my cursor moving by any chance? To be able to point at this, can you?
Yes, your cursor.
Okay, good. So this little this hole can crop up just by chance near a small angle. What Fred and Andre proved is that these little features are spurious, and that if you increase the rate of balls by some constant factor, all such features appear. All these little holes will not persist. New form, but only the ones that persist will correspond to the real homology of the underlying compact set, which you're trying to understand in the first place. Okay. Nice way of getting rid of that smoothness, and it's also a natural way that persistent homology arises in a setting which is kind of different from, I think, the original context in which it was considered. It's looking at a filtration which has just two, right? It has a small scale and a large scale. And at the same time, there was another cell which had the same feature, which was the work of Vin De Silva and Rob Greist on homological sensor networks. In the slide, I've laid out just a version of a homological sensor network problem. The things we try to do in this was to focus on this problem and to draw the connections between the homological sensor network results and the feature size results. And as we're only going to use one parameter, alpha, here. So familiar with the original work on homological sensor networks, you may recall that there's a bunch of different radii. There's the strong coverage radius and the weak coverage radius and fence radius. There's many of these radii, but we're just going to have one parameter, alpha, and it's going to be the radius of these balls that we're looking at. And the goal is, given some compact domain, A, boundary B, we've got what we'll call sensors, but really that's still points in the domain. And the so-called fence nodes, well, these are just the points in the of the points of P that are within distance alpha of the boundary. Now I'm going to use this notation throughout. This superscript alpha, or the superscript on a set, is going to be the offsets of that set. So it's union of ball radius overall in that set. So coverage area P alpha is just a union of alpha radius balls set at the points of P. The main result was of Greist's work, at least the dimensional version, said that if you have no coordinates and you know the boundary or the neighborhood of each point, you know which sensors are nearby at, say, a radius something like alpha over square root of 2, and then maybe ones are within distance 3 alpha. Certify or check give some proof this set D minus some. So you took the set D and you shrunk it in by alpha. You can at least guarantee that this set is covered by, so it's contained in P alpha. It may be that it's covered and you aren't able to provide a proof, but if you get a proof, then you know it's really it really is covered. And that proof or that certificate is computed by looking at d-dimensional persistent relative homology of Rips complexes. Any questions before I move on? So, just a reminder, I'm sure many of you are familiar with Rips complexes. Sometimes they're called victorious Rips complexes. They include of a metric space, and that's how they're used. But they're defined is if you're just given a finite metric space, so a set of points with distances, and for any particular scale alpha, you can compute a complex a space subset where this is our less than or equal to, say, 2 alpha. So let me draw a picture. This is easiest to see. Here's this alpha. And so if I have a pair of balls that intersect, then we'll add the edge. And here's a larger scale. If I have some new edges, and anytime I have all 3 edges, I'll add the triangle. If I have all 6 edges of a tetrahedron, so clique in this graph that I form, I'm going to add a simplex, and that's the Rips complex. And we have filtration if there's a sequence of them where they're nested by inclusion. And by scale parameter, you naturally get a filtration. And for this talk, at least, we'll have filtrations of just 2 complexes. So 1 scale included in a larger scale. And to the homological sensor network problem, this is like saying, okay, the complex associated with this higher neighbors in, say, alpha over square root of 2, and I look at it included into the Rips complex I would get by looking out to distance, say, 3 alpha. It is a version of the topological coverage criterion. So it's based on the paper by Rob, but it's not how I wrote it, because I've kind of taken, I've tried to make it stay in a way that's closer to the way we stated our results. So it's going to look very similar to some of the results, because I've projected it onto, at least I did their vocabulary onto our vocabulary, and I've also taken out most of their constants and replaced them with just a single constant. So what they proved was a little bit more nuanced if you're considering actual sensors. But the domain and sitting in RD and it's connected. B is its boundary, and the assumption is that that boundary is some smooth manifold with infinity radius at least 4 alpha. You give alpha if you're familiar with a different term. Okay. The D, the relative Rips complexes. So I've got a complex for the point P, which is our full point set at the scale alpha over square root of 2, and get relative to the Rips complex at just the boundary points or the fence nodes. And I look at what persists as I increase that radius up to 3 alpha. Anything persists. In fact, you guarantee you have coverage. This which is this in the Rips complexes is something you really compute without coordinates, only knowing the neighborhoods and which points are near the boundary. Okay, so you can check, and if it turns out to be non-zero, then you can really say that at least the shrunken version of the domain, where we shrunk it by 2 alpha, are by the sensors. Okay, so this that we prove in our paper, which is very similar, but you'll notice that we can get rid of some of the geometric assumptions. If E is just any set in E with boundary B, you look at the zero-dimensional homology of the domain shrunken by 4 alpha. If included into the domain shrunken by only 2 alpha, all right, the homomorphism on the homology, if that isomorphism, which is really saying that when you shrink by 4 alpha, and then you went back out to shrinking only by 2 alpha, that all the components persist. Right? Those are only and exactly the components that persist are the components of those spaces. And if that's an isomorphism, and now yet we have the same topological coverage criterion, we're going to check this additional relative homology of complexes into a larger pair of Rips complexes. And now we just check that it's equal to the rank of J star. So J of connected components. In this theorem 1, connected, it's just assumed to be 1. And so it can only 1 or 0. And 0, then it's and you have to check that it's equal to the rank of A star. And if that's true, then you have coverage. Now, you may think, well, we don't know what D minus B for alpha is. So what that means, we can't tell if we have how many components it has. But if you just have some higher assumption, whether it be that it's connected or that you know how many components there are, or at least you've sampled from every component, then you have to be able to check and compute this criterion to set coverage. So here, the J star, this assumption that isomorphism is replacing the smoothness condition of the boundary. So that's going to be a new shape condition. So it replaces what was the geometric condition with something that's now really stated in terms of persistent homology. It says that the persistent zero-dimensional homology of the domain when is stable when you just think from the boundary. All right. So if you cover criterion, and the conclusion is that we get coverage. So tricks that we're going to use, these are not new tricks. These are in fact exactly the tricks that are in the De Silva and Grice paper. First is use Alexander duality. So if I have this union, if I have balls here, I can look D-dimensional cohomology. That's going to be isomorphic to the zero-dimensional homology of these complement spaces. So when I write a bar over a set, I mean its complement in D sphere. In this, if you consider the blue here is complement of the domain, and B is boundary, and the complement of B, well, the white, say, is our boundary. This tan and blue line are both the complement of B. Then when I am looking for the zero-dimensional homology of D bar, it's just about the D-dimensional cohomology of D comma B. And this is really useful because it means that we can take statements about D-dimensional homology or cohomology and just talk about zero-dimensional homology. In particular, we can just make simple trig arguments about connectivity. This, I don't recommend it, but sometimes it's useful to also think about this zero-dimensional relative homology. Because D is really the boundary of D, this is the zero-dimensional homology of D minus the boundary. And I've done the domain boundary, but we'll do the same thing with offsets of the domain and offsets of the boundary. And we'll also do with offsets of the point set relative to offsets of fence nodes, which is actually what the picture I have here. And the way is that if there's some piece of the domain that's not covered, or at least the shrunken domain, like of here, this killed this entire component. Because at any point in the yellow to the blue, previously the yellow from the blue, but if there's some part that's not covered, the path, and that path is a singular one simplex, which has one end in D bar, another end in B. So this whole yellow component just dies. It actually won't form treatment in the zero-dimensional homology groups. Is, as I mentioned, that if we have some small bubbles or spurious features, we're going to use persistence to eliminate them. And in fact, that's the crux of the whole proof, is to show that any other features you might see, any other, in this case, D-dimensional or zero-dimensional features in this relative homology of the complements, that any features has to die when we look at a large enough scale. this pretty well known, the interleaving of rips and Cech complexes. And then just show it now because it allows us to always just talk about geometry and not about simplicial complexes. So at the top, you'll see this top line is exactly the homomorphism that we as part of the topological coverage criterion. We're looking at this pair of Rips complexes into this pair of Rips complexes. Just you can include these Rips complexes into corresponding Cech complexes. And this across the top, our TCC, fast through this map of Cech complexes. And each pair of Cech complexes is in homology is isomorphic to a pair of offsets. So P of Q alpha. So the union of balls of radius alpha around P relative to the union of balls of radius alpha around Q. And by the persistent nerve lemma, in diagram on the bottom, this rectangle commutes. So if we want to bound the rank of this map on top, it's enough to bound the rank of just the offsets, and which is very for another reason, in particular, because P alpha really is the coverage domain. So we have to translate between Rips complexes and the coverage domain. In fact, we're going to get a result directly about the coverage. And it's most of the arguments much easier because it does we can just apply metric arguments directly. This is both ideas are already present in this paper, but they kind of apply it later, and I kind of want to apply it first so that we have to think about, for instance, the shadow of a Rips complex. Is where you take the Rips complex of a set of points, and then you look at its embedding in the Euclidean space and try to reason about that as a geometric object. These sets are much kind of easier to work with geometric objects. And in fact, most of the statements we'll make now will just be in terms of this this inclusion of pairs into a larger pair of offsets. And again, if you want to map this onto the vocabulary of that original work on sensor networks, you would see that out here is that strong radius, and this 3 alpha is like the weak radius. Let us give a sketch of how this proof works. Just as pair spaces, we get inclusions between this pair of offsets into the larger pair of offsets, and I can also include it into the offset of the domain relative to the offset of this boundary, and the offset, a larger offset of the domain relative to a larger offset of the boundary. Just a sequence of inclusion maps, and if I look at it in d-dimensional cohomology, then Alexander duality says I can write pretty much the same diagram dualized, so all the arrows the other way now, and all the spaces get complemented. This map here, H0 of B4 alpha bar, D4 alpha bar, in H0 of B2 alpha bar, D2 alpha bar, is just that we had before. This map J star is exactly the same J star we had up here. Let me just see if I can jump back to it. It is the same J star, although here it's written, of course, as D minus B4 alpha. And it's hard to see that the dimensional homology of this space is exactly zero-dimensional homology of D minus B4 alpha. Assumption that, or main hypothesis that we have to make about the underlying, this sort of assumption which replaces smoothness is going to be that this map across the top here is an isomorphism. Bottom, you'll recognize this is of our inclusion of the strong radius into the offsets of the weak radius. Okay, this is what we're going to compute, or at least bound using Rips complexes. These inclusion maps, a map between the image of J star up here and into the image of I star on the bottom. It's going to be our homomorphism, and the main work of proving that this or topological coverage criterion is correct is just to prove, well, first lemma is just that if this map is injective, then you really do have coverage. There's nothing new in this. This is, in fact, exactly the proof that appeared in Christ, and it's the one I sketched by how if there's a little piece that's not connected, so if you look at the contrapositive of this statement, if it's not covered here, then some point which is not covered, which has some component in here, and so this map cannot be injective. It will have some component in the image of J star, some persistent connected component. If it has a point that didn't get covered, then when it drops down into the image of I star, it will die. And so, so that is that if we have an injective map here, then with coverage. So that's a good start. But the other side of this is we have to check that we have anything extra. And so what I mean is that that phi star in fact is also surjective. A star is an isomorphism. It really is going to be surjective. Okay. Any questions? I can't see any of you, so I can't hear any of you. So I'm hoping that we're still broadcasting, and I'm a sketch of the proof of lemma 2. So we want A star as an isomorphism, then this is going to be surjective. Start with some point x, which is in P alpha minus Q alpha. Actually, it should be P alpha minus Q3 alpha. This is going to be a point. Then the persistent, it's an image of I, so I star, so it's which persists in it's a persistent connected component our bridge domain. So in our ends of balls here. So it has to be in P alpha, but it's not in Q3 alpha. So this is a typo, because that'll just be 0. It wouldn't have persisted. So it's equivalent homology is in star, and we'll show that there's some element image of J star that maps. Okay. This point is far from the boundary, so if it's in B2 alpha bar, so if it's at least 2 alpha away from the boundary, then again we can look. That means it must be non-zero element in H0 B2 alpha bar, D2 alpha bar up here. This is an isomorphism, then it actually lives in this image, and therefore there's some element of image of J star that maps to X. Okay. So that it must be the 2 alpha of the boundary, so let's let Y be the point nearest to X on the boundary on B. Okay, so the distance from X to Y is less than or equal to 2 alpha. But since X is not in 3 alpha, it means that this ball of radius 3 alpha, this big ball, is empty of points of Q, and so the smaller ball radius alpha around Y is then also empty of points in Q. That's just the triangle inequality. And so Y in Q alpha bar. But that means that Y must be in P alpha bar. If Y was in the P alpha, it would be a point within distance alpha. But since Y is in the boundary, that point would have to also be in Q, but not in Q alpha. So y is in P alpha bar, and so it implies that our x really was 0 in the image of I star, because I can take a straight line segment from x to y. That's a scalar 1 simplex, and its boundary is just x, because y lives in P alpha bar. A quick sketch, but this is in fact the crux, and it's qualitatively different from what happens in the Rice paper for a couple of reasons. One is that the most important one is that the arguments happen directly the rest of homology. And if you look back to the De Silva-Grice proof, they take the relative homology and they look at it under the connecting morphism, and then they look at the d-1 dimensional homology in just the boundary. And you don't have smoothness. See, like for instance, this zigzaggy shape here actually has quite large, even weak feature size could be arbitrarily large. But it has a sample of points that are all close to the boundary. But the balls, that sample, form a cycle which can actually persist for a long time. And that's in their paper, actually have a note that says you probably need this smoothness condition, or if you got rid of the smoothness condition, you have to, you would set factors degrade as the sharpest feature gets sharper. So it would mean that you would have to look at an even larger increase from the scale on the left to the scale on the right in order to kill any features that appear just in this thick part of the boundary. And the reason the way they use the smoothness here is that the boundary to be smooth so that inside the offsets of the boundary you could get out quickly. Actually, if you notice, what we did is the opposite, is that we took an x, which was in the offsets of the boundary, and we got to the boundary as quickly as possible. And that seemed to be a key insight. And so if you try to take the proof from the original paper and just push it through with the kind of geometric perspective we've taken, you will get stuck here. And doing proof directly on homology turns out to make it, I think, as well as at least general, because you don't have to consider extra conditions on the boundary. At this beginning, set you up to see this connection that the total coverage criterion and this weak feature size based approach to homology inference connection. And at first, they like converses in the sense. The total coverage criterion says that compute the homology, or you can test if you have coverage. And the inference based on weak feature size says something like, well, if you have coverage, that is, if you have a good sample, the homology. The analogy seems to break down without the smoothness because, in fact, the weak feature size was invented to eliminate assumptions about smoothness, whereas the the homological sensor networks papers seem to imply that the smoothness was necessary. So now we see it's not. We can try to state these two results, which we're going to do on this slide, in a way that makes it clear the extent to which they are conversely related. So if you have this domain D, and let's say for now it's locally contractible set as boundary, and the weak feature size is at least as greater than 4 alpha, which is the boundary, and I have my subset Q, which is the set of points near the boundary. For any integer k, we let hk be this homomorphism. Right? It's the homomorphism induced on k-dimensional homology, inclusion of P alpha Q alpha into P3 alpha Q3 alpha. Now, the two statements, first, that if D is a subset of P alpha, and we would say D is completely covered by P alpha, then, but just by looking at the image, you can actually infer the homology D comma B. This is how Fred and Andre stated the result, but it follows pretty easily from their result. And this one is now the logical sensor network result, which says if the HD is equal to homology of D comma B, then have this coverage. The difference is in the have to have the entire space and homology for every dimension. Second one, you only need to know the d-dimensional homology and infer that of some shrunken version of the domain. So D minus B2 alpha is covered. So they're but not quite converses. And pretty fast here, but just to wrap up, I am going to just way you can put this similarity to use. So call it certified homology inference. The idea is that, let me start keeping the slide for a second. The idea is if I know the homology, or I only know the zero-dimensional homology, the number of connected components, and the shape is sufficiently nice, let's say it has bounded weak feature size. Check if there's coverage. Well, I can get coverage a smaller domain. But if I do the smaller domain, then hope to get coverage to infer of the rest of the space. There's some checks to doing this correctly, because if you're only assuming that the space has bounded weak feature size, then what you have to do is you have to throw out points that are too close to the boundary. So these are that we can tell which boundary, in fact, that maybe on scales, and we'll say that U beta is the set of points P minus B beta. So that the points in P whose distance to the boundary is more than beta. And we're going to look at offsets of these subsets of P. If a sample from D alpha, and so considering the case where the sample might not be just in D, but it's at least within distance alpha, and criterion. So I know that the shrink by 2 alpha, I'm covered, then for constants that satisfy some conditions, as long as the weak field size is sufficiently large, then you can do homology inference, again, by looking at the rank inclusion of some sets of subsample into offsets of a larger subsample. Because coverage criterion doesn't give you exactly what you need to apply the Chazal-Luthier results directly. That's why I like to do this subsampling. But then this, by the same Cech rips interleaving type arguments, you can, or bound this rank in fact, for bounded weak sets, you can actually compute this rank from persistent homology for thus get the homology of the underlying domain for all K. So the say is that you use this TC to certify the coverage, assuming that you just knew, say, the number of components, and then you can use that if to compute the higher Betty numbers by an algorithm which is very similar, would have done anyway, but now you have a guarantee. Or if the coverage criterion comes back negative, if the rank of that including Rips complexes isn't equal number of connected components, then you have some evidence maybe you don't have enough samples to do homology inference in the first place. You can do away perhaps with the assumption that you had a good sample, and instead you just check manually whether or not you did have coverage, and then proceed from there. Okay, I'm going to thanks slide, but maybe coverage, is that all right? If I take questions, is it all right if I here so that I can see any questions?
Thanks a lot.
Okay. Thanks, Liz. All right. Hey.
Don, I just want to make sure I understood. So you had this partial correspondence, this partial if and only if, I suppose?
Yeah.
And that's where you were using at the end to say you can test the 0th dimensional homology to see if you have good coverage, and if so, then you know you can do homology inference.
Yes. Yeah. Technically, I guess what you test is the d-dimensional homology, but yeah.
Okay.
Yeah.
So, I see. So you had a homological criterion in one dimension, and if that's satisfied, then you know that you can actually cover all the homology groups.
Yes.
Yeah, cool.
Yeah.
This is Beck. Can you show up your slides again? I have a question regarding one of the slides.
Sure.
Sorry, bring it back again.
No, easy.
So if you go back, okay, so this my first question is a little bit confused by that example with this big bikes. I'm basically, I guess my imagination was pretty limited here. Am I imagining this is a 3D? What is this sort of very twisted object that you're showing?
Yeah, this is a 2D thing. Imagine that this is the boundary. I haven't drawn the whole shape, but the shape is below. This is the upper boundary. So there's just a set in 2D, and its boundary. This is one piece of its boundary. Bottom side. It's below. Look closely. You'll see points are sampled below that curve.
This is a complete 2D object, and then you happen to have an interesting for that position as you way you doing it. I think now I have a better idea what's going on here. Okay, so my follow-up question: if you go back to last but 3 slides, to go back, this one, yes. So the first stand is hold to say that if there's sort of inclusion, then I have a much stronger thing to say that my homology is going to be isomorphic to the image of a K for all dimensions. And then the thing is that if I only know isomorphism at the least dimension, then I have the TCC condition. Is that correct? Hear you. Lost you. Sorry. Oops. Sorry. Hey guys.
They repeat or Don either. So.
I don't think I managed to get my, but I couldn't hear him. How can we tell him he can't hear us?
I just read Don's lips. Don said that he can hear us, but we can't hear them.
I think both of us lost audio, or we are the. Can't hear. Okay, so looks like Henry and I are okay.
You can narrate from names, just try to provide what people.
Liz, one.